Hello and welcome. I'm Dr. Stoddard from Danville Community College, and this is Lecture M for Natural Science 102. I'm trying a different format for today's lecture. If you do like this format of lecture, please give a like in the YouTube or a comment on YouTube and let me know so I can continue doing this or go back with the old way. Electricity is today's topic. We are in the physics module, and so we're going to be talking about electricity in this lecture and the next. So let me tell you about this weird thing called the Amber effect. So to many people nowadays, electricity seems like magic. But electricity is not magic, and it can be understood and explained with science just like any other natural phenomenon. Electricity was a mystery for thousands of years, however, and what people noticed was that you could obtain this thing called amber and rub it on a cloth, and then the amber would magically seem to be attracting bits of paper or attract hair, kind of like a magnet. Now, amber is a tree sap that's hardened over the years, and this piece of amber, if you look carefully at it, has a fly trapped in it that's been fossilized for many years. You can see the wing, the body, bits of the leg there. And so this material in particular shows the amber effect, but nowadays, now that we can synthesize plastics, that's a very common material that's going to show this effect as well. So that's what was first noticed. Along came J.J. Thompson. Now, we've talked about J.J. Thompson before. He discovered the electron. But there's more to the story here. He also contributed to electricity. Now, he discovered that all atoms and materials are made of negatively charged particles. And he also experimented with electricity and found out that these negatively charged particles are responsible for the flow of electricity. So therefore, he named the word for these particles electron from the Greek word amber. Okay? So if I told you back, a few weeks ago that the electron is named after the Greek word amber, you might be like, huh? Why, what? Well, that's because the Amber effect demonstrated this electrostatic mystery that wasn't solved until J.J. Thompson came along and discovered the electron and then tied it in with the electricity, and then so he called the electron the Greek word amber. Okay, I thought that was pretty interesting. Now, let's talk about charges. Electricity has everything to do with charges. It's important to review atoms for a moment. Remember that atoms are neutral overall, but they're made of charged subatomic particles, okay? We've learned that electrons have a negative charge or a charge of -1, and protons have a positive charge or charge of +1. Now, normally, atoms are neutral because they have an equal number of protons and electrons. For example, lithium has 3 protons in the nucleus. Okay, so it has a total +3 charge there. And lithium also has 3 electrons outside the nucleus. So there's a -3 charge out there. So since we have a +3 total charge in the nucleus and a -3 charge total outside the nucleus, they balance, and so the net charge is 0 for a neutral lithium atom that we normally find as an element. But we will see in a bit how atoms can lose or gain electrons to become charged. So remember that the nuclear model of the atom has all the protons and neutrons all crammed in the very compact center of the nucleus. It's shown in this drawing here as a red dot. So we're not going to focus in on the neutrons and protons in that very small compact space. Now, most of the atom is empty space, and it's occupied by these electrons that are whizzing around the outside of the nucleus. And remember, these electrons are negatively charged, and they're loosely held by the atom. And they can be easily removed and transferred from one object to another through friction, through electrochemical reactions, and other processes, okay? Ionization occurs when an atom loses or gains electrons. So that's the process, we call it ionization, when atoms are losing electrons or maybe gaining electrons. Now, if an atom loses or gains electrons, they can become an ion or an atom with a net charge. Okay, so again, neutral atoms have equal numbers of electrons and protons. Ions have unequal numbers of electrons and protons, so they're charged. Charged atoms are called ions. Okay, let's look at this figure. Here we have a sodium atom. Sodium is capital N, small a. It's element number 11 or atomic number 11. So it has 11 protons and 11 electrons. And the starting charge is 0 for a neutral sodium atom. You can see a bit of the map there if you squint. We have 11 protons, we have 11 electrons, so that's equal to a 0 overall charge. 11 minus 11 is 0, okay? The starting charge is 0 for this neutral sodium atom, but if one electron is lost, it now has an unequal number of protons and electrons, and since it has more protons than electrons, it's going to be positive, okay? Exactly one more proton makes the ion plus 1 overall in charge. If you look at the math here, we have 11 protons, which are positive 1. We have 10 electrons, which are minus 1. So overall, there's 1 extra proton, which gives it a plus 1 extra charge for the whole thing. So that's called an ion. So that's a sodium ion, okay? So atoms are not always neutral, and this explains how electrons can be transferred from one object to another, and things can pick up electrons and become negative, or lose electrons and become positive, okay? If you forget this, it's useful to remember the joke. 2 hydrogens walk into a bar, and one says, "Hey, I think I lost an electron." And the other hydrogen says, "Are you sure?" And the hydrogen atom says, "Yeah, I'm positive." So if you lose electrons, you become positive. Here's a sodium atom losing 1 electron, and it becomes positive. The opposite of that is true. If an atom gains electrons, it's going to become negative. You may notice, I do for sure, during the cold, dry winter months that you get static shocks frequently from touching doorknobs or combing your hair. If I take my sweater off, there's all this crackling and sparkling and static discharge, okay? So here we have a plastic nylon comb rubbing a person's hair in a barber shop. Now the hair loses electrons and becomes net positive, and the comb gains electrons and becomes net negative. And since these objects have a charge that is not moving, or it's static, we call it electrostatic charge. So remember that we cannot create matter, we cannot create electrons out of nothingness. The electrons have to come from the hair and be transferred to the comb. If the hair is losing electrons, it's becoming positive. If the comb is gaining electrons, it's becoming negative. Electrostatic discharge is when the electrons return to the object they came from. Okay, sometimes this returns the materials back to their neutral states. We call this electrostatic discharge. So lightning is a very dangerous and dramatic illustration of electrostatic discharge. When electrons flow from clouds, between clouds and the ground, in a sudden moment, there's a tremendous amount of heat and light that's given off. Okay? A simple example of electrostatic discharge is when you shuffle your tennis shoes with rubber soles on a carpet floor, and your shoes, and therefore your body, pick up extra electrons, and this static charge is held by your body until you touch a metal doorknob, for example. And when you touch the metal doorknob, the excess electrons or static charge return to the floor in a sudden transfer of charge that we call electrostatic discharge. Okay? Now the feeling for me is uncomfortable, but I only receive a temporary shock on my fingers or my hand. But it's unexpected and it's surprising and it kind of hurts a little bit. So this is the Amber effect for 2020 and beyond. In this demonstration, what you can do is you can take a plastic or nylon or rubber comb or brush and rub it through your hair a few times, okay? Now, already have on the ground some bits of paper that you've torn up. It could be tissue paper or normal paper. Make sure the squares are kind of small, okay? And now here, before we get into what happens, remember that the electrons transfer from the hair to the comb, okay? So the comb now carries a net negative electrostatic charge. And the ordinary bits of paper have a random distribution of charges. But when the comb is brought close to the paper, it causes some of the negative charges to be repelled from the paper, and this redistribution of charge is called induction. I'm not going to require you to memorize the vocabulary word induction. And so the positive charges on the paper are attracted to the negatively charged comb, and this can result in pieces of paper actually being stuck or drawn or float through the air or stand on end on the tabletop in the direction of your comb. I saw a funny Google image that I searched for. There was a cat, I guess, that was combed, and then this cat ran through some little bits of paper, and all the paper had stuck to the cat. So the cat was covered in this little confetti. Okay. Now, how do we measure charge? The measurement of charge is given by the fundamental metric system unit of Coulomb. Remember, there's 5 fundamental metric units that we have for different quantities. Coulomb is for charge, and we give it the capital C. Please don't confuse this with degrees Celsius, since we don't have that little circle or degree symbol next to the capital C. Now, an electron has a very, very tiny charge, and a comb that's charged by static electricity has a very, very small charge as well. But a lightning bolt will have a larger charge. So we know that the quantity of charge can vary, and we can measure this amount of charge in the metric system, or the unit called coulombs, okay? Now, we abbreviate the charge with the symbol small q. So, for example, if we have plus q, we indicate that we have some positive quantity of charge. And if we write minus q, we indicate that we have some negative quantity of charge. This might seem a little confusing, so let me explain a little bit better. For example, with temperature, we abbreviate that with capital T, okay? Capital T is the symbol or abbreviation for temperature. Now, if we're talking about degrees Celsius, that's the measure or the unit that we're using to quantify that temperature. In a similar way, we have Q and capital C, okay? So Q is the symbol, or just how we designate we have some kind of charge, okay? But capital C is how much charge, or the quantity of that charge, okay? Now, let's talk about opposites and like charges repelling and attracting one another. So you may have heard the expression that opposites attract. This phrase is, I see, for example, people in the mall or something that are just completely opposite. I'm like, how can those two people be together? But it works, all right? And it seems to be a human character that we're kind of attracted to people that are very different from us, okay? This phrase is also apparent in physics, where it's known that a negatively charged electron is attracted to a positively charged proton. Remember, we've talked about the atom and how it's all held together. The nucleus is positively charged because of the protons in the nucleus, and the electrons on the outside of the atom are whizzing around. Somehow they don't go flying off, they stay together because of this electrostatic attraction. The negatively charged electron is attracted to the positively charged protons, so they're all held together in the atom through this Coulomb attraction. Okay? Now, a negatively charged balloon is attracted to each strand of hair that is positively charged. Okay? So if you look at this image here, you can see that the hair is appearing to stick or be attracted to the balloon. Okay? And that's because of opposite charges attracting. Now, this is really cool. You may have seen this in a museum. They've got these shiny metal spheres and maybe a rubber belt in there and a motor that's going on. And this thing is called a Van de Graaff electrostatic generator. Here it's removing electrons from this person, and as the whole body becomes positive, you can see their hair standing on end. Okay, it's just sticking up. Well, why is that? What's going on? Well, each strand of hair has lost electrons, so each strand of hair is positively charged. Now, adjacent hair strands are also positive, And since similar charges, positive and positive, repel each other, the hairs are going to repel away from each other. And so this is why the hair appears to be floating, okay? That's the way the hair can get away from each other. The sensation that you have when you're touching this metal sphere is rather interesting. If you've ever been in a thunderstorm and the hairs on the back of your hand or your arm start sticking up, you know you need to seek shelter immediately because there's a tremendous amount of electrostatic charge being built up on you, the ground, and the clouds directly above you. And there can be an electrostatic discharge in the form of lightning at any moment. This slide lists the 4 fundamental things we need to know and remember for my class qualitatively about Coulombs Law. Now, Coulombs Law is a mathematical formula that I'm not even going to write down. We're just going to look at it qualitatively. The first thing to review is that opposites attract. So a +1 charge and a -1 charge will have an attractive force towards each other, okay? The second thing to remember is that like charges repel. Now, there's 2 possibilities for that. Here we have a +1 charge and a +1 charge that will be forced away from each other or repel each other. The second possibility is when we have a -1 charge and a -1 charge, and those 2 will be repelled away from each other or forced away from each other. Now, here are some details that are new here, okay? In the third bullet, we have the closer the distance between the charges, the greater the force. So I've got some illustrations to illustrate that. I've got a negative Q that's in blue and a positive Q in red that are attracting one another. But they're very far apart, so the force between them is very little, as indicated by the length of the arrow. In the bottom figure, we have the -Q in blue and the +Q in red that are very close to each other. And because they're closer to each other, they experience more force or more attractive force between each other. And this is how we indicate it by the length of the arrow. The arrow is longer, which means the force is greater, okay? So you've heard the expression, opposites attract. Well, let me introduce you to a new one. Long-distance relationships don't work. Right? So when the charges are very far apart, they're not really strongly attracted to each other. When they're close together, they're strongly attracted to each other, okay? I missed this lecture by just a few days for Valentine's Day, but you get the idea. What's the fourth point here? The fourth point here is that if the value of the charge is greater, then the force will be greater, okay? Let's go back to the analogy of opposites attracting. I've gone to the mall and seen some people that kind of look a little different. Oh, okay, they make a good couple. And then I see a couple that's just really just 100% opposite than the other person. They're just so different, but their relationship is so strong and close, and they're just such a great couple. And it seems like the more opposite people are, the more strongly attracted they are towards each other, sometimes in a good way, sometimes in a bad way. So +1, -1, there's a strong attraction to each other. +5, -5, that would be a tremendously greater attraction towards each other, okay? Opposites attract, closer is stronger, more charge is stronger, okay? Now, how do we actually measure charge and the flow of electricity and stuff like this? Well, let's start getting into this. This is my electric current, okay? Electric current is defined in amperes. We just always call it amp for abbreviation, okay? Now, electric current is defined by the quantity of charge that travels through something per unit time. We could be talking about a wire or a light bulb or a fan or a vacuum cleaner, okay? So, remember, in electricity, we call the quantity of charge a coulomb, but we call the flow of charge an amp. An amp is equal to 1 coulomb that travels in 1 second, okay? So an amp is a whole bunch of electrons, and if that flows through a wire in 1 second, then we call that an amp. So it's the flow of electricity. This is analogous to the current or flow of water. Okay, so water current or water flow. In this picture, it might be hard to see, but we've got a garden hose on the ground, and there's water flowing out of it. Now, we could say that this hose delivers 2.5 gallons per minute. 2.5 gallons is a quantity of water, and minute is a unit of time. Now, we could measure this by taking an empty bucket and start filling it up. Start the stopwatch, start filling up our bucket, and after 1 minute, hit the stop button, and then measure how much water we have. And if it was 2.5 gallons, we would say that the flow of water is 2.5 gallons per minute. We do something similar with electricity, but really not quite. So over here on the left is an electric meter. There's all these dials and numbers and everything. This is an old electric meter that you can find on the side of some houses. Nowadays, most of the meters are digital or smart meters that relay the information back to the company. If you look at the word kilowatt hours up on the very top, there's that black line. And just below that is a disc, a metal disc that's orientated kind of horizontally, and it's got little black markings on it. The way this old meter works is that if somebody turns on maybe the oven, or somebody turns on the air conditioning and it's going at the same time, your house is going to require a lot more electricity or current, and that disc is going to be spinning a little bit faster, okay? Now, what's interesting is if you turn off all the lights, you turn off all the lights in your house, you turn off the oven, you don't use your hair dryer or anything, nobody's using anything in the house, you can actually see this disc still turning, and we call this phantom current. Your microwave clock is still on. Your radio clock is still on. Maybe you have some chargers that are plugged in to different walls in your house that are still using a small amount of current, even though nothing's being charged. Maybe your smoke detector is plugged in, and so on and so forth. And this is called phantom current. It uses quite a bit of electricity, and it's interesting to read more about it if you're interested in saving money and knowing about that. Let's talk about the current flow. We, of course, don't have garden hoses and water. We're dealing with other kinds of materials. So the most common conductor are metals such as copper, aluminum, or silver. And these materials allow charges to flow easily since the electrons are loosely attached and flow freely. Okay, so any metal you can think of in the periodic table is generally going to be a good conductor of electricity. Materials that do not allow charges to flow easily are called insulators. Insulators are usually used to keep wires separate from each other. If you go to your vacuum cleaner and you plug it in, you'll notice that there's that rubber cord. Okay, the extension cords you use in your house are rubber because we don't want the electricity in the wires to come into contact with your skin, which would cause charge to transfer and you would get shocked and so on. Okay? Common insulators are rubber, glass, or plastic. Now, semiconductors are rather interesting. Examples include silicon and germanium. These are metalloids that touch the staircase of the periodic table. And they have properties that sometimes conduct and sometimes insulate. They are used in computer chips, solar cells, and cell phones. Now let's take a closer look at amps. Okay, remember amp is a current flow. And if you're trying to fill up a bucket of water, you want to turn your hose on as fast as possible. If you want to fill up your bucket very slowly, you would turn it with a trickle. Now, when you're charging your phones, you want to charge your phone as fast as possible normally because you don't want to wait around for it to get charged. Now, we all know that certain phone chargers work better than others. Here we can see the product information on the left for a basic 1 amp charger for older Apple iPhones. You barely can see it on the image probably, but I've circled 1A. It says 1A, and there's this line coming off of it. Now, this information indicates that this charger can pump out a current of 1 amp, okay, or 1 coulomb per second. On the right is the certification label for a better 2.4 amp charger for iPads or newer iPhones that are capable of this fast charging, okay? And I've highlighted the 2.4A with a little circle there. And this again means that it can pump out an even higher current of 2.4 amps. Most, but not all electric equipment around your house, such as toasters and vacuum cleaners and Oh, look at the hair dryer if you have a hair dryer, and so on. These will have current ratings listed on the rear device of the plug. Okay, so usually on the hair dryer or the plug or the charger, you look on the back of it and you'll see some information about amps. So take a look at some of the things around your house and see what the amperage or current rating is for various devices. Thanks for watching. Please like this video, give a thumbs up, consider subscribing to illustrate to me how I'm helping people around the world with this video. If you like this lecture format a little better than the other standing up by the flipboard you can see over my shoulder there, please let me know in the comment section below. Thanks and have a great day.